The model we have created here consists of two troughs, a ramp and a sphere. We are going to try to make the sphere roll down the two troughs and then rebound off of the ramp. To achieve this, we are going to use the rigid body dynamics command. To get the ball rolling in the required direction, we have animated the sphere to drop onto the first trough in the direction we wish this sphere to roll, as shown. First select the Utilities icon and then select the Dynamics button. We will then go down to the Dynamics roll down menu to set up our parameters. First we must select the New button and then input a unique name for our simulation. We will then select the Edit Object List button. Then in the dialog box we can highlight the objects that we wish to include in our simulation. Once selected, we can hit the OK button. If we now click the Select Objects in Simulation button, it will highlight all of the objects. The objects not highlighted do not influence our animation. Selecting the Edit Objects button will open out a main dialog box where all of the physical properties for each of our objects are set up. If we first open the pull down menu, we will be able to see the list of objects within our model that we selected for this simulation. When we select an object, the first thing we do is set up the miscellaneous dynamics controls. The two options are Use Initial State and the object is immovable. Basically, this is asking us whether the object is fixed in space or whether the object moves in space. The object within our scene is fixed, therefore we select the second option. If we now select the Assign Object Effects button, we can select any effects used in our scene to influence our object. In this example, we will assign the gravity space warp that we have placed within our scene. We must also set up the Assign Object Collisions dialog box. Here we can select any object within our scene that will affect the object that we are currently setting up. In this example, the only object that influences our shoot is the spherical ball. In the Physical Properties parameter, we can set up the static and sliding friction values. This will affect how the ball rolls down the chute. We will now set up all of the other immovable objects within our simulation. Again, that you will notice that we set up the same parameters as the original object. We will now set up the parameters for the spherical ball. First reselect the Use Initial State radio button. This is not an immovable object. We can then set up the Recalculate Properties parameters. In this example, we will select the Every Frame option. We will then select the Mesh option for our collision test. This means that our object will react relative to its mesh shape rather than as a boundary box, cylinder or sphere. Again, as with the other objects, we must assign any effects and collisions within our simulation and set up the static and sliding friction parameters. As the ball is the animated object, we will set up the density and bounce properties. The lower the bounce value, the less the object will react when hitting one of the other objects within a scene. Finally, we must set up the Calculate Properties using parameters by selecting either vertices, surfaces, bounding box, cylinder, sphere or mesh solid. The mesh solid will calculate the geometry's true volume and mass, whereas the bounding options calculate the extents of the box, cylinder or spheres. In this example, we use the sphere bounding box. We can now select the OK button. If we test our animation, we will see that none of the parameters have yet been assigned. We must first select the Solve button to calculate our simulation. Checking the Update Display Radio button will update the viewports as the simulation is being solved. Before we select the Solve button, we must first set up our start and ending time. We can also change the calculation intervals. The timescale variable allows us to slow down or speed up the simulation. It is a linear scale factor. If we now select the Solve button, the simulation will be calculated. This can take a little time, so we will open the same model where this calculation has already been done. If we now play the animation, you will see that the sphere rolls down the two chutes, is then deflected by the ramp and finally drops back to the ground.